right, good morning everybody, and welcome back to microprocessor course, lecture number 6. In today's class, we are going to start chapter number 2, where we talk about a specific microprocessor. We're going to talk about 8086 microprocessor, its architecture, addressing mode, instruction set. There we're going to start doing some practical task to understand how a microprocessor works. But before we start today's class, I'm going to check if everybody is present in today's class. We're going to start by class number 5, 5-1, number 2, number 3, number 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, class 5 number 20, Yuri, 21, class 1, 5, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 30, class 530. Are you Peter? Class 6 number 1, number 2, number 3, number 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 14. Class 6 number 14, 15, 16, 17, 20, 21, 22, 23, 24, 26, 27, 28, 29, 30, P21, 6, 15. Good, okay. All right, so in today's class, as I said before, we are going to learn a specific microprocessor, its architecture, addressing mode, instruction set, and we're going to start doing some practical examples to help you understand how a specific microprocessor works. So before we start, I wanted to remind you that a microprocessor is a program-controlled semiconductor device which fetch instruction from memory, decode instructions to understand what does this mean, then execute them. Execute instruction. Now here it has to get the instructions from memory, and the second task for a microprocessor is to decode the instruction to understand what it has to do about the instruction fetched from the memory. For example, if you have this add instruction, content from register 2 to register 1, microprocessor needed to decode this instruction to understand what it has to do about this. For example, we have this opcode, which means add is an opcode, and we have two operands, R1 R1 and R2. So it has to decode using the control unit also to get which instruction has to be executed in which order. Then execution, to execute the instruction fetched from the memory. Now, it's used as a central processing unit for our computer system. It's like a brain of the computer system. Our microprocessor is like the main brain for the computer system. Now, we're going to have a look to a functional block of microprocessor. We have arithmetic logic unit. We talked about this in the beginning. But to remind you, this unit is there to perform arithmetic and logic operations. After that, we have flag registers. We have many registers in our microprocessors. These are various conditions of the result, which have to store the status. The status bits, we call them flags in the flag registers. Another key component that we needed to talk about is registers array. These are really small memory integrated in our microprocessors. Really smallest. These are the smallest memory in our computer system, but they are really fast. They are very, very fast. Next, we have another key component, PCIP, programmer counter, instruction pointer. This one is there to generate what we call the address of the instruction. Address of instruction to be fetched. Address of the instruction of the next instruction to be fetched by the microprocessor, and that it has to be sent through what we call address bus. If you still remember, we have data bus. We have data bus to transit data, and we have address bus to transit addresses from memory, and we have the control bus, which are there to transit control signals. Now you see that here, once this PCIP generates the address of the instruction, it has to be transit through address bus to the memory. The next one is instruction decoding units. This is a unit that's being used by our microprocessor during our instruction decoding cycle to understand what the instruction does mean to it, to get to know which operation it has to compute based on the instruction on the hand. The next is timing and the control unit. We talked about the timing and the control unit because microprocessor has many instructions. We have to get these timing and the control unit to generate what we call control signals for internal and external operations of the microprocessor to avoid competition, to allow operation to be done in a specific order. We need this control and the timing unit. So this is a functional block of a microprocessor. Functional block of microprocessor, and these are the main component of the microprocessor. Now, let's have a quick view about 8086 microprocessor. 8086 microprocessor is a 16-bit microprocessor. That means that the data width is 16. We have talked about 16-bit microprocessor, 32-bit, 64. When we talked about Intel microprocessor, and we got to understand what it does mean. And originally, it used what we call HMOS, high density metal oxide semiconductor. Now, it had 29 transistors, 29,000 transistors. This is also a key features for our 8086 microprocessor, and it had 40 pins dual in package. So it does not have internal clock, and the external one is asymmetric clock source with 33% duty cycle. The address bus is 20-bit address. 20-bit address. This is also another key feature of 8086 microprocessor. That means it can address up to 2 to the power of 20. That is 1 megabyte of memory space. It can address up to 2 to the power of 20. That is 1 megabyte of memory space. So addressable memory space is also organized into different banks. Each bank is 12 KB. Is 512 KB. And the even one, which is the lower one, we have the even one, which is the lower one, and the other one is the higher bank. And we have addresses line 0, which is used to select which bank has to be used. Is even or is odd. We use, or it has also 16-bit address for input-output devices. That means it can generate up to the power of 16 addresses. That is 60K addresses. It has to operate into modes, minimum mode, and maximum mode. We're going to see when it is selected to work in the minimum mode, what it does mean. When it is selected to work in the maximum mode, what it does mean. So these are the key features of our 8086 microprocessor. Now, we're going to talk about 40 bits of 8086 microprocessor. We have 40 pins that you do see here depicted by this picture. For example, we have this AD0 to AD15, and these are bidirectional pins. Why? Because they needed to transit data and the address. That's why they are bidirectional pins. Now, we have, when these AD lines are used to transmit memory addresses, the symbol A is used instead of AD. So when it has to transit memory address, we use A instead of D, A0 to A15. When data are transmitted over AD lines, the symbol D is used. For example, if we need to transit data through AD line, we need to use the symbol D, data. We use D0 to D7, for example, or D8 to D15. The next pins are high order addresses bus. These are multiplexed with control signals. You can see them from AD16 to AD19. These are very important pins which are multiplexed with the control signals. Next we have the BETE, which is fast high enable status. This is used to enable data on the most significant half of the data bus. For example, you have D8 till D15. These are the half of data bus. Now, 80-bit devices is connected to the up half of the data bus by using BHE pin, this fast high enable. Now, we have this active low signal, which is then multiplex with S7. You see, this PHE is multiplexed with S7. Now we have minimum and the max pin, which is pin number 33. This pin is very important to indicate which mode the processor operates in. Pin number 33, which is pin max or min, is there to indicate in which mode our microprocessor 8086 has to work in. Now we have lead pin, which is our pin number 32, and this is very important because it is used for lead operation. For lead operation, when it is active low, it is there to be used for read operation. The next pin is pin test, which is pin number 23. And this is used when we need to test the wait instruction. The wait instruction. Now, 8086 microprocessor can get in a wait state after execution of the wait instruction. Once it has got the wait instruction, we will have to sum the 8086 using this test pin. This test pin, when it's made lower by an active hardware, that means our 8086 can get in what we call wait state when we have the wait instruction executed. To resume it, we need to use the test pin, and we need to make it low by using an active hardware. Now, the main function for this pin is to help in synchronization, especially when we have external activity to the processor internal operation. So this is a very important pin, which is used to resume our 8086 microprocessor after a wait instruction. Now we have a LED pin. This is like acknowledgement from the slowest device, or the memory, when it has completed the data transfer. Now, we know that our microprocessor interacts with different devices. For example, it has interacted with the memory, read the data from the memory, or to store the result to the memory. Now, this LED pin is used to send acknowledge from the slow device. As you know, the data transfer rate is slower if you compare to the speed of microprocessor. That means the memory, for example, we have to use this pin to send acknowledge to the microprocessor to indicate that it has completed its data transfer. Now, the signal is made available by the device, and it is synchronized by 8284A clock generator to provide what we call input. So this signal is active high. The next pin is reset pin. Now, sometimes we need to cause our microprocessor to terminate immediately is current activity. So this reset pin is very important if you want to immediately stop the current activity of microprocessor. Now, this signal must be high, at least 4 clock cycles. Reset pin is used when you want to stop immediately your microprocessor 8086 is current activity. The next pin is the clock. The clock pin. This is a really important pin because this provides the basic timing. The basic timing for microprocessor operation and the bus control activity. It is asymmetric square wave with 33% duty cycle. Now, this clock pin is also important because it does provide a basic timing to our microprocessor. The next one, interrupt request. Interrupt request. This is pin number 18. This is like a trigger input. This is sampled by the last clock cycle of each instruction to determine the availability of the request. Now, if any interrupt request is pending, that means that the processor will enter the interrupt acknowledge cycle, and this signal is active high and it is internally synchronized. The next pin is interrupt, as we have seen. This is the number 18. We just talked about it. This is to determine the availability of the request. And if there is any interrupt request, that means that is pending. The processor will have to get in what we call interrupt acknowledge request. Now, the next one is the min and the max pin. Min and the max pin, they are 30 pin, and this is used to select in which mode our microprocessor 8086 needs to work in. Now, the 8086 microprocessor can work in two different modes, mode minimum and mode maximum. If it is in the minimum mode operation, that means the microprocessor do not associate with any other coprocessor. It has to be in uniprocessor settings. Minimum mode, that means it has to work alone. It has to be in uniprocessor settings. When it is in maximum mode, this means that our 8086 microprocessor can work in multiprocessor setting. That means it can have a coprocessor configuration. Now we have minimum mode, min mode. That means it has to be in uniprocessor setting. And we have maximum mode. To indicate that our microprocessor can work with multi-processor or coprocessors. Now, we're going to have a look when our microprocessor 8086 is set to work in minimum mode or maximum mode. Now, when this pin is high, that means that our 8086 microprocessor needs to work in minimum mode. And it operates in the maximum mode otherwise, when it is in lower. Now, minimum mode. Now, if you try to see pin 24 till pin 31, they will be selected if our mini mode is active. Now we have pin 24 till pin 31, which are selected. That means it is in minimum mode. It is in uniprocessor setting. Now we have our pin 27, which is bidirectional, as you can see here. And we have data transit and or receive. Now here, it is used to generate a signal from the processor to control the direction of data flow. That means it has to be data transmit or receive. The next pin is data enable. Data enable is pin number 26. This output from the processor is used as output enable for the transceivers. Now, the next one is pin number 25, address latch enable, ALE. This means this pin is used to demultiplex the address as the data line using external latches. The next one is MO, memory input output pin, which is the pin number 28. And this one is used to differentiate, to make the difference between the memory access and the input access. Now, we know that the microprocessor has to interact with the memory to read the data from the memory or to store the data to the memory or to interact with input output to get input from the input device or provide the result to the output devices. So we need this memory input output pin. This one is there to help the microprocessor differentiate memory access for memory access or input output device access. Input output device access. Now, for memory references instruction, that means this pin is high. To make this memory access, the pin has to be high. For input output instruction, it needs to be low. So this pin, memory input output pin, which is a pin number 28 in minimum mode, is there to help the microprocessor differentiate memory access and input output access. For memory access, for memory references instruction, it has to be high. Otherwise, for input output, it has to be low. For write control signal is pin number 29. This pin is very important to write control signals. And it is asset row when a processor writes data to the memory or input output. Now, writing data to the memory, our pin number 29, write, is there to be used to write control signal, and it is assessed low when the processor writes data to the memory. When the processor writes data to the memory, this is asset low. Our pin number 29, write, is going to be asset low. Now, interrupt acknowledge. When the interrupt request is accepted by the processor, the output is low on this line. Now, we're going to learn more details about interrupt, but I want you know that the interrupts are very important in the computer system. Sometimes an input-output device needs to have a immediate attention from the processor. Then there will be an interrupt request from the device interrupt request from device to microprocessor, and the microprocessor will send an interrupt accept to allow the device to provide the data or to have a control of the bus based on the interrupt is granted or is denied. We're going to learn more about interrupt in computer system. What are their function? How does our microprocessor handle interrupt? Now, maximum mode. Now, we have seen that our microprocessor 8086 can work in minimum and maximum mode. And now it's time to see when it is set to work in maximum mode. During maximum mode, the min and max pin is grounded. That means is logic low. Now, again, the pin number 24 to 31 are assigned. That means they are active. We have this pin 26 till 28. These are control signal pins, and you see their settings to allow the microprocessor to be in interrupt acknowledge, or to have the right input output, or to have halt or read memory, write memory, passive or inactive. So these control signals are used by 8086 microprocessor bus controller to generate timing as well as control signals. So they are decoded as shown in this table. We have different control signal status for S2, S1, S0, and we have the machine cycles on the other hand. For example, if we have S0 set to 0, S1 set to 0, and S2 set to 0, we have interrupt acknowledge. This is interrupt acknowledge. When we have all these control signals set to 0, we have interrupt acknowledge. Now, if we have S0 set to 1, and S2 and S1 all set to 0, we have what we call lead input-output port. We have S2 and S1 set to all 0, and we have S0 set to 1. Then this is what we call lead input-output port. For inactive or passive, we have all control signal S1, S2, and S0 all set to 1. That means we have the microprocessor in passive or inactive status. Now, next one, we have queues. We have pin number 24, 25. We have the processor which provides the status of the queue in this line. We have the status of the queue in this line. So that means the queue status can be used by external device to track internal status on the click. So the output of these queues are also depicted in this table. We have QS1, QS0, and when QS1 and QS0 are all set to 0, that means we have no operation. We have no operation at all. When they are all set to 1, that means this is a subsequent byte which is sent from the queue. Now, if we have the QS1 set to 1 and the QS0 set to 0, this means amped the queue. Now we have the pin number 31, 30, which are bus request, bus granted. Now these requests are very important, and they are being used by local bus masters to force the processor to release the local bus at the end of the processor is current bus cycle. These are bidirectional pin. If you try to see pin number 31 and 30, they are all bidirectional bus because they needed to send the bus request and get back the bus granted. Now, these pins are very important if the microprocessor wanna handle the bus request. And the request on GT0, we have higher priority than GT1. Now, what is bus masters? Bus masters. This is when we talk about input-output. Now, we know that there are many devices connected to our computer system. And when a device needs to use a bus, it has to send a bus request to the microprocessor. And the microprocessor will send back a bus granted. Once the bus request has been accepted, the input or the device, we have to control the bus. We have to initiate data transfer without microprocessor is controlled. So this brings down to what we DMA, direct memory access. So this is something that we're going to learn in more details when we learn about bus arbitration. That means we have many devices. To avoid the competition about the bus needs to be requested from the microprocessor. So the device which needs access to the bus or which needs the control to the bus, we send a bus request to microprocessor, and the microprocessor will handle the bus request. Once the bus request is accepted, the device will be able to initiate data transfer without microprocessor is controlled, and this is being done through direct memory controller. Now we have lock pin. This is our pin number 29. This is very important and is activated by the lock prefix instruction. We have a lock instruction, and this remains active until the compression of the instruction. It has to remain active up to the compression of this instruction. So 8086 output low on the clock while executing this instruction. So why this lock is very important? Because it's there to avoid the bus masters to gain control of the bus system. So this is very important. It has to be there to avoid the bus masters to gain control to the bus without getting bus granted by our microprocessor. So we are just done with functional block of processor, and we just learned about 40 pins, and we have described some of them, their function, and now it's time to have a look on 8086 microprocessor architecture. Now we have two important parts. We have bus interface unit, BIU, on the right side, and we have the execution unit on the left side. So here we have BIU, which is there to fetch instruction from the memory. It has to fetch the instruction from the memory. It has to read the data from the memory, or input-output, and write data to the memory or to the input-output. For execution unit, on the other hand, is there to execute the instruction that has been fetched by our BIU. So So this means these two, they work separately. The bus interface unit is there to fetch instruction from the memory, is there to write data to the memory, or read the data from the memory. But the execution unit is there to execute the instruction that has been fetched by our BIU. Now we have execution unit, which includes accumulator register, base register, data register, stack pointer, base pointer, destination index, source index, and so on and so forth. We're gonna discuss in more details about these registers. And for BIU, bus interface unit, it includes code segment, data segment, stack segment, extra stack segment, and we have address generation module, because our data segment, code segment, stack segment, all these segments, they are 16-bit, and our physical memory is 20-bit, so we need this address generation module when we want to found a physical memory that a specific segment 22. Now, let's have a look on BIU, bus interface unit. This is the one. We have code segment, data segment, and stack segment. All these segments are 16-bit. We have code segment. We have code segment, data segment, stack segment, extra segment. We have code segment, data segment, stack segment, and extra segment. So these segments, they are all 16-bit. Physical memory is for 8086 microprocessor, if you still remember, it is 20-bit. Now we need this address generation to find out the memory location wanted by each of these segments to get 20-bit memory address. So how are segments organized? We have our physical memory, and these are the memory addresses. We can have segment arrays one after another in serial from segment 0, segment 1, segment 3, and so on and so forth, one after another. So we can have segment arrays in our memory like this, one after another, segment 1, segment 2, and so on and so forth. Also, we can have the segment partially overlaps. If you try to see here, we have our segment 0, and at the end of the segment 0, we have segment 1, then we have segment number 2, which overlaps, partially overlaps with segment number 1. That means here we have segment 1, segment 2, and we have our segment number 3 here, which is partially overlaps with segment number 2. This is partially overlaps. This is your 5-minute break. Please take your break. We're going to resume class after break time.